Hi everyone, so today I'm going to be talking about an algorithm called the particle filter, and what this algorithm does is, imagine you're in a dark room with nothing but a couple of sensors to give you some observational data, and what you can do is, using these sensors you can roughly locate where you are in the room without having to see anything. And so, as an example, we can see this is what the particle filter looks like on initialization. You can see where we truly are located is on the red dot. Where the particle filter thinks we are is at the blue dot. And as you can see in the background, there's a ton of particles. And basically, it's an iterative algorithm, and so after each iteration, we are going to narrow down our particles to roughly around where we actually are located. And so how we do that is we go through each particle, all 1,500 of them in my example. We ask each particle, if my agent was truly at the position you are describing, then what is the probability? What is the probability that my agent is actually at the position you are describing? So we go to this particle, ask, well, how likely is it that we are here? We go to the next one, how likely is it that we are here? And so on. And the reason we do this is because we want to resample our particles for the next iteration. And so using weights described by the probability that our agent is actually at the specified position of each particle, we can resample our particle and get a distribution that is a lot closer to where we actually are. Now, the big question is, how do we find this probability? Well, we have sensor data, like I described earlier, and in my example, we have a distance sensor that tells us the distance to the closest wall. And so, in this example, we are going to get a distance of roughly 1. So where we're located at the bottom right here, we'll get a distance of roughly 1 from our sensor. And so, all the particles that would read a distance of roughly 1 will be more likely than particles that do not. For example, in the middle right here, you can easily, it's obvious to see that these particles would not have a distance of roughly 1, or the sensor, it's not likely that the sensor, if the robot was at that location, it's not likely that the distance sensor would give us a reading of roughly 1. And so these particles will slowly be eliminated throughout the iterations. And if I'm going to show an example, you can see that slowly the ones in the middle are being eliminated because the particle is located near the bottom. But that leaves us with a square rim of where the particles could be, are pretty likely to be, because all of these particles around this square rim right here it's pretty likely that the sensor will read 1. There is some noise to the sensor. I did account for that in the code as well, so it doesn't have to be exactly 1. But yeah, so we'll get like a square rim of plausible particles. And how we narrow it down even further to where the particle actually is we have to keep moving around, getting different sensor readings. And once we can move around a lot, it'll be a lot closer. The range of the particles will be a lot more narrowed down to where we actually are. So as an example, you can see there's a lot of particles on each side. If I move towards the left, you can see the particles on the right start to disappear. If I move up, you can see that the particles down below start to disappear as well. And now our particles are roughly all very close to where we actually are. And so that's really neat. And so obviously some practical applications of this are in robotics. To locate your robot. You're not too familiar with the way your robot moves or anything, so you need to use some sort of localization algorithm to keep track of where you are, and maybe you have the layout of your environment, so that would be very helpful as well. And this algorithm works for noisy movements as well, so if I were to add some noise to our movements, as you can see, it's still keeping it still has a pretty good estimate of where we are.